So this application example is an indeterminate structure which is subjected to an internal torque, as you can see in the figure over here. So you have this shaft over here, A to B, part of it which is solid and part of which is hollow. So maybe we just go ahead and mark that. So this is the solid part and this is the hollow part, right? And where you're having at the exactly at the center between this length of 125 125, at the center of this member you have a torque of 120 Newton meters. So the question asks that to find the support reactions, you are given the diameter of the solid core, which is 25 mm, and the hollow core has an inner diameter of 15 and an outer diameter of 25 that you have over here. Okay. So for this one, first let's go ahead and so we are trying to find the support reactions. First let's go ahead and draw the free body diagram for this entire member that is there. So if I have to represent the member, maybe something like this over here, where this is my end A and this is my end B, and say the point at the center where my torque is being applied is this. So let me call this point as C, right? So C is somewhere here in between. C is here. Now at this particular point C, you have this torque of 120 Newton meters that is being applied. Now follow your right hand rule, that where the direction towards where the arrow of the moment points, that will your thumb will point towards the direction where you should mark the double arrow for the torque. So in this particular case it points towards B. So let's just go ahead and mark the torque here, that is represented by these double arrows, remember. So this is the applied torque T, which is 120 Newton meters. Now as a consequence of this applied torque, you will have the reaction torques at the ends A and at the end B, and let me just mark these reaction torques as something like this. This is my reaction torque TA, and at the end B also I have the reaction torque TB. So the basic relationship from equilibrium, some torque equilibrium relationship, I can write it out as my TA plus TB is equals to the applied torque T. So that is one relationship that I have over here. So let me maybe mark this as relationship number 1. Now how do I find TA and TB? So that's the question, that is the support reaction. So the question asks you that how do you compute your TA and TB over here. So what is the equation of compatibility which we are going to use? You can see that the end A and the B, they're clamped, so they are not going anywhere. So your overall the phi that you have, the angle of twist between A to B, is going to be 0, right? But you may have the internal phis, your C, the point C over here may move, but if you say draw a straight line from A to B, that straight line does not move anywhere. So the overall phi for that entire structure, phi AB, is equals to 0. Now so how do we compute this? So the phi AB, if we have to just write it out, that we have our phi from A to B is equals to the phi AC. This is again in drawing analogies with your axial loading, the total delta equals delta 1 plus delta 2 and so on, and it depends what the final delta is. If you have a clamped support with an axial load, that is 0. Here for the torsion case also, if you have a clamped ends, then the total rotation is equals to 0. This is phi AC plus phi CB over here. Now how do we compute phi AC? Phi AC is for this point, and phi CB is for this portion of the shaft over here. Now as you can see that we always draw the sections where we have the discontinuity. So from here to here, so I have an applied torque at the point C. So I am going to go and take a section, maybe section 1 over here and a section 2 over here. So maybe if I have to show in this 2D diagram, this is 1 and maybe this is 2. Now for the first portion, so for the AC part, so if I have to draw the free body diagram there, how do I, so along where I cut the section, how do I represent that? So I represent that as, I represent that as something like this, where at the left end, as you can see, I have my reaction torque TA, and at this particular end I must have an internal torque. So let's just write that TB. internal, which is going to be equal and opposite to sorry, this is not a reaction. The internal torque must be equal and opposite to the torque Ta that you have over here, simply from equilibrium, right? Now these two torques are pointing outwards, these are pointing away from this particular shaft. Now let's look at this guy over here at this. So this is for section 1. This is what I drew over here, is for that one between A to C. So this is from A to C, right? Now for the part B to C, if I draw the section from here to here that I have, right? So for that, what I get is that at the right end I have my reaction torque, which is TB. So at the where I am cutting this section over here, which is this point, at this particular point I am also going to have an internal torque here. So this internal torque in this particular case is going to be equal and opposite to TB here, right? So this is for my section 2. Now for the part AC, how can I write my phi AC? We know that, so I am just going to split these two guys over here, like this one and write the individual equations for both. So what I get as my phi AC, remember the torsion formula, phi equals to TL divided by J times G. So phi AC will be equals to the T internal in the section AC times L of AC divided by J of AC times G, right? Let's say it's made of the same material, so G is the same for both the AC and the CB over there. Okay, so that brings you, because T internal in the portion AC is nothing but equals to this A over here, because this is for the section AC. So that is equals to TA times LAC divided by JAC times G. Okay, so that gives me my phi AC over here. Now the next one is my phi CB. So let's go ahead and write that as well. Phi CB comes out as equal to T internal CB times length of CB divided by JCB times G. Now here is an important point to note. Look at the direction of previously what we had. TA was pointing outwards, whereas your TB and T internal B, that is T internal in this can be, is pointing inwards. Now as is customary, that remember for the axial loading also what we had, that when it was the forces were pointing outwards, the tension was positive, inwards it was negative. For when we mark torques as well, when you have the torques which are pointing outwards, then you typically mark them as positive. If it's pointing inwards, the torque and the corresponding phi becomes negative. It is analogically similar to tensile and compressive. So here this is going to be minus of TB. So here I should write a minus right here as well, minus of TB times LCB divided by JCB times G. Okay, so I have written down what are the internal torques that we have over here. So now I'm going to have to use this compatibility, because I know my phi AB from here to here is equals to 0. So that means my, if I take that condition over here, so that what I get, my phi AC plus P of CB is equals to 0. So that gives you the relationship that TA, so that means TA times LAC divided by JAC times G plus of minus TB times LCB divided by JCB times G is equals to 0. Okay. Now here This is an interesting problem where the shear modulus doesn't matter, because if it's made of the same material over here, this G goes to 0 over here. So this G, if you take it on the right hand side, that becomes equals to 0. Now also one more thing to note over here, that for this problem, your length of AC and length of CB is the same. So this LAC I can replace by L, and this I can replace by L, where LAC equals to LCB equals to L, right? And this also goes to 0 because this is a common parameter that you have in between, these two terms of on the left hand side. So this further simplifies your expression, that TA divided by J of AC plus of minus TB divided by J of CB equals to 0. Now this is one more relationship that you got over here. So this is your relationship number 2. You have one relationship 1 over here. Now here you need to calculate what is going to be your JAC and what is going to be your JCB, because JAC, remember, it's a solid core and JCB is a hollow core that we have. So now if you go ahead and compute the JAC, so the JAC for this part, this guy over here is going to be pi over 2, and the diameter of this one is given as 25. So it's going to be 25 by 2 raised to 4, whereas your JCB here is the hollow core. So this is that hollow part which has an internal diameter of 15 and the outer diameter of 25. So JCB is going to be pi over 2, 25 by 2 raised to 4 minus 15 by 2 raised to 4. So once you have these and then you use the relationship, this one and this equation over here, you have two equations and two unknowns. I will not go ahead and punch in the numbers and solve it. Please go ahead and solve it. I will give you the final answer that you will get after you solve these two equations and find out the two unknowns, which are the two reactions that we were supposed to find. Remember, this TA and the TB. So your equations are in terms of the unknowns itself. So what you will get as the final answer is your TA will come out as 64 Newton meter and your TB will come out as 56 Newton. Okay. So I hope this overall problem was clear for this indeterminate shaft. So you had a indeterminate structure with a torque at the center. We use the equation of compatibility to find out the reaction torques.